Good. So today's topic is min-cost flow tracking. I've argued that this is one instance of a linear programming problem. And the question is, why is it a linear programming problem and not an integer linear programming problem? And this is what I'm trying to answer in part in the next few minutes. So we need definitions first. An integer square matrix is called unimodular if its determinant is plus or minus 1. An integer matrix, not necessarily square, is called totally unimodular if each and every submatrix has a determinant which is either 0 or plus 1 or minus 1. And by the way, if a matrix is totally unimodular, then all its elements must necessarily be 0 or plus 1 or minus 1. But that's not necessarily true for plain unimodular matrices. And so, where to read up on this? Well, typically in books on combinatorial optimization, and this is one that I like a lot. But if you want the shorter version, I very much like this set of slides from a discrete optimization course by Mark Utz, and I reference his slides in the following. We have a few theorems, namely, if a linear program with constraint matrix has a constraint matrix A that is totally unimodular, and if this right-hand side B is integer, then the feasible region has integral vertices only. Let's go back to the picture that we saw before. So here, this was, some constraint matrix A, and you see the corners. If I look at the corners of the feasible region here, the corners have some fractional coordinates. I mean, it would, there's nothing, or it would be it would be by chance only if one of these corners was integral, if it coincided with one of the red dots that we have here. And well, we've learned that the optimal solution of a linear program, or one optimal solution, is always given by a vertex of this, by a corner of this feasible region. So if I have a linear program that has a feasible region, all corners of which are integer, then, well, the linear programming solution is also an integer linear programming solution. Or in other words, if I solve a linear program, if I solve this, and if I find that the optimal solution x is already integer, well, then I don't need to include this extra constraint. And then I don't need to work harder than I already have, because I have already solved, apparently, the associated integer linear program. All right, so Theorem says that if I have such a linear program, if constraint matrix A is totally unimodular, then as long as B is integer, the feasible region has integer vertices only. And in that case, as I've just argued, geometrically, the ILP reduces to a LP and can be solved efficiently. It turns out that the incidence matrix of any directed acyclic graph is totally unimodular, or a slightly different formulation here, a min-cost flow problem with integer edge capacities, which, as long as it doesn't have unbounded capacity, has an optimal solution with integer flows on its edges. And now the only proof that I wanted to sketch briefly, because this is somehow, in this series of theorems, this is, I would say, the one where the integrality really comes in, is this one here. And I don't have time to walk you through it in detail, but I give you, the course overview. So given an integer square non-singular matrix B, and if I require that I have a linear system of equations where Bx equals B, then my solution x is integer for any right-hand side B if and only if B is unimodular. And now we need to prove the if, and we need to prove the only if. So x can be rewritten as the solution of this system of equations. And then there is something called Cramer's rule, which is shown on the right-hand side, which says that the ith component of the solution is given by a ratio of determinants, namely the determinant of a matrix B in which the ith column has been replaced by the right-hand side B of the system of equations. And if we look at this matrix, well, it has all integer entries, and we were requesting that the right-hand side also be integer, and then this entire numerator is going to be some integer number, because the sum of products of integers is integer. The denominator, well, we said that B is unimodular, so by the definition of modularity, we know that the determinant is either +1 or -1. So in other words, we're going to divide an integer number by either +1 or -1, which is an integer number, and hence this is enough to show that x will be integer for any integer right-hand side B and unimodular matrix B. All right, and the only if direction makes an argument that I will not be able to do in the 0 seconds that I have left. The handwriting is a little bit poor, but the steps that I've made in following, they're very small, so I think you will be able to follow this. You will need these concepts of total unimodularity for the bonus exercise, but not for the normal part of the exercise. Summary: pure flow problems, whereby pure I mean standard max flow or min cost flow problems, are described by LPs, by linear programs with totally unimodular constraint matrices, and if I give them integer edge flow bounds, so integer right-hand sides in addition, this will guarantee me integral solutions of the associated linear program, and hence pure flow problems can be solved to global optimality very efficiently by using just linear programming and not integer linear programming. Great.